Okay, good morning, everyone. Today is a review for Friday's midterm, so no new material, just covering some of the kinds of questions that you might be expected to answer on the midterm. That is a slight hint. Okay, so we are going to go through discussion of functions and gradients to start with, thinking about Lagrange multipliers. We're then going to talk a little bit about volumes when we have a solid revolution. And then finally, if we have time, linear systems. We might not get to the linear systems question, but I put it on there anyway to give you guys some additional practice if you need it. Okay, so starting off with functions and gradients. So a reminder that everything on the midterm, the midterm covers everything since week 6 and onwards. So for some reason the screen is behaving a little bit strangely. There we go, a little bit better. Everything from week 6 onwards, that started off with looking at directional derivatives. We moved through thinking about maximum and minimum of functions. I'll give you one hint, there won't be any data fitting on this exam, so you don't have to worry about this data fitting for this. Lots of discussion there. I don't know if that's a few or not. Okay, so after thinking about critical points, and guys, a little bit quiet, please. Guys. Okay, so after looking at critical points, let's see, what did we move on to after that? Can anyone remember? It's so long ago. It's like, what did we do after that? After looking at critical functions, data, we did volumes. That was next, wasn't it? So yeah, we'll talk about volumes a little bit. Then we spent quite a lot of time looking at linear systems, and then recently non-linear systems, but those non-linear systems, remember, are not going to be on the midterm. They will be on the final. Okay, so let's go all the way back to thinking about some of the earlier stuff. So thinking about what happens if we have a function. Here we're just given a mathematical function here. A function of 2 variables that represents a surface if we plot that in 3 dimensions, where the height of that surface is, if we call this z is equal to f of xy. The height of that surface is the function value for a given set of coordinates x and y. If you can imagine your x and y are some points on a flat surface like a table, and then your surface, your function value is the height above that. Okay, so we often want to find the maximum and minimum values of a function. This could be anything. We've been through examples of where, say, a farmer has to put different nutrients into the soil to get out a certain yield of a crop. So you might want to maximize his yield, and therefore we want to know the critical points of this function. But there also might be cases where there are constraints. So there was an example of putting nitrogen and phosphorus into the soil. You can't just keep pumping lots and lots of nitrogen and phosphorus in the soil. There might be some sort of physical constraints, but there also might be economic constraints as well. Okay, so the first step to solving this problem here is we need to find our partials of f, and we can do that using the product rule. So if we want to look, I'll help you out with the partials here. So our partial of f with respect to x, here we need to use the product rule. Remember, when we take our partial derivatives, we treat the thing that we're not taking a derivative with respect to as just a constant. So that means I'm going to bring this y out the front. Partial of this with respect to x. So we'll take x times by the partial of e to the minus xy with respect to x. So we're going to have a minus y coming out the front of this, because that's treated as a constant, times by e to the minus xy. And then now we take this and multiply it by the derivative of this. The derivative of x with respect to x is just 1. We multiply that by e to the minus xy. That's just our product rule. Okay, so that simplifies down to, let's see, yeah, minus x y squared e to the minus xy plus y e to the minus xy. We can factor out a y and an e to the minus xy. So we end up with y e to the minus xy times by 1 minus xy. Because this is symmetric, if we change our x's and y's around to get the same thing, our partial f sub y is going to be just switching the x's and y's around everything here. So we're going to have x times by 1 minus xy e to the minus xy. So these are our two partials. If we wanted to just find the critical points of this function, ignoring this constraint, we would set both of these partials equal to 0 and then solve for x and y that satisfied that condition. Remember, both of these would have to equal 0. Because we've got this constraint, though, we need to take that into consideration. So I'm going to let g of xy be my constraint. So we've got our constraint up here, x plus y is equal to 1. That means I'm going to write this as x plus y minus 1. Okay. In the IQ, a lot of people wrote this. G of xy is equal to x plus y is equal to 1. But our constraint is equal to, has to be equal to 0. Okay, so we need to put everything on the same side. We can also tell from this straight away that if we think about our gradient of g, this is, remember, the vector of partial derivatives. We're just going to have 1 here. Because these are both linear in x and y. Okay, so now we need to use our method of Lagrange multipliers, which I'll just abbreviate that. We need to have the gradient of f. Remember, that's just going to be the vector that has our partials of f with respect to x and y. Is going to be equal to some lambda, some constant, times by the gradient of g, which we've just worked out. Okay. At this point, I'm going to let you guys have a go at solving the rest of this. Remember, we need to split this into different conditions. Because this is a vector here, there's a vector on the left-hand side and a vector on the right-hand side. We can just equate the x and y components of these vectors, and that'll give you two different conditions. And we also have our constraint as well to think about. We want to then eliminate our lambda. So we have an equation in terms of x's and y's, and then factor in our constraint. Okay, so see what you end up with. Have a go at working through that to find your x and y that satisfy this question here, and then to find the maximum value of this function, you plug those values back into the function. Okay, have a go at doing that. I'll walk around and answer any questions. Okay, so we have this vector equation here, and that means that we can break it down into different components. So if I think about my x component, I'm going to have f sub x is equal to lambda times g sub x. Likewise, I'm going to have my f sub y is going to equal lambda g sub y. And then we also have our constraint as well. Okay, so what is f sub x? Well, we had it up above. Where was it? It was here. So that means that y e to the minus xy times by 1 minus xy is equal to lambda times by g sub x. G sub x is just going to be 1. So we just have lambda on that side. And over for our y component, we have x e to the minus xy. 1 minus xy is equal to lambda. So now at this stage, we want to equate these equations. Something I tend to do here is I give my equations some numbers and then describe what's going on. So always try and make sure it's clear what you're doing. So use words to describe what you're doing. In case you make a mistake, it gives someone who's grading it an idea of what's going on. If you just start writing down random numbers or it's kind of all over the place, it's difficult to track what's going on, and then it's difficult to give you guys marks, okay? So for example, here I would say equate equations 1 and 2. So it's clear what I'm doing, okay? The reason I can do this is because we have the same thing on the right-hand side. If, for example, we had something like lambda times x here and a lambda times y, just for example, I would need to make these things the same by multiplying the equations by some value. Okay, so I would multiply this equation on the left-hand side by y and this equation on the right-hand side by x. I have to do the same to the left-hand sides of these equations, then I would be able to equate them. Okay, so you can only equate them if the right-hand sides are the same. And if they don't, you just need to modify them accordingly. Okay, so equate these equations. We get y e to the minus xy times by 1 minus xy is equal to x e to the minus xy times by 1 minus xy. At this point, we can do some cancelling. E to the minus xy is always positive, so we can cancel this. Can we cancel anything else? Have a show of hands who cancelled the 1 minus xy's. Okay, what happens? We don't know what x and y are. What happens if xy is equal to 1? If xy is equal to 1, then these brackets are equal to 0, and then you've just divided by 0, which we can't do. Okay? So at this stage, we can't do any more cancelling, because this could equal 0. Okay, so what does it tell us? Well, to get these things equal to each other, we either have that y is going to equal x, or y is going to equal 1 over x. Okay. But now we can go back to our constraint. So remember, our constraint was x plus y is equal to 1. I'm going to call this little thing here equation 3 and this one equation 4. What can we do? We can substitute one of these into our constraint or vice versa. So let's substitute 3 into, I'll call my constraint 5. So substitute 3 into 5. That gives me x plus x. If I eliminate the y's, it's going to equal 1. So x must equal a half. And y is equal to a half. What about if I substitute y is equal to 1 over x into my constraint? I'm going to get x plus 1 over x is equal to 1, which we can't do. It's impossible. At least it's impossible with real numbers. Okay, if x is less than 1, then this is going to be less than 1, but this is going to be greater than 1, and they're both positive. If x is greater than 1, then the one on the left-hand side is going to be greater than 1, and automatically it's going to be greater than 1 as well. Okay, so we can't do this. It does turn out, you might have ended up with this answer anyway, that y is equal to x, but mathematically we can't be sure of that until we can't eliminate this 1 minus xy. We have to go through these steps to make sure. Okay. Okay, so we have our condition, x is equal to a half, y is equal to a half, and that's saying that our function f of xy has a critical point when x is equal to half and y is equal to half, or rather, it has a critical point subject to this constraint here, x plus y is equal to 1. So our maximum value of our function, remember this could be something like a crop yield, maximum value subject to a constraint when xy is equal to a half. And we're asking the question, what's the maximum value? That means we just substitute these values here back into our constraint, and into our original function, sorry. So we look at a half. So we have xy is a half times y a half, e to the minus xy, e to the minus a half times by minus a half, which is e to the minus a quarter over 4. This is the maximum value of this function subject to the constraint. I've used the example of crop yields. This could also describe something like fitness. So you could have a surface that describes the fitness of organisms in a population, but there might be constraints on, say, if these are different traits, but these traits are somehow correlated. Say it's something like body size and wingspan in birds. You probably wouldn't get a bird that has a tiny body with a huge wingspan because there's some constraints between these things, okay? So there are lots of cases where we might care about looking at maxima or minima subject to certain constraints. Yes? Mm-hmm.
But your actual still right why is the number x times cancels out? Will you still get a deduction or?
You would pretty get, like, you would lose a partial mark there. Okay. Yeah. Because xy might equal 1, in which case you would have 1 minus 1, which is 0, and then you'd be dividing by 0. So when we're canceling things, we're dividing both sides by whatever that thing is. So if we divide by 0, then we're in trouble. Okay. As it turns out, you did end up in the end with y is equal to x down here, but that was only because we'd verified that if you substitute y is equal to 1 over x, which is what we had here, into our constraint, it wasn't possible. Yeah. This was essentially just by rearranging this. I have skipped some steps here. The reason I've skipped these steps here is because it's a slightly longer rearrangement. I wanted to go. You want me to go through? Yeah, I can go. I can post the longer thing here. I wanted to make sure we've got time to do the other questions, though. Okay, so that's why I've not gone through that yet. Okay, let's move on to solids of revolution, because I want to make sure we try and capture as many different types of questions as we can in this review. Remember, a solid of revolution, we can describe, say, a slice through an object if it has rotational symmetry. If we want to work out what is the volume of that solid, we can maybe describe it by some curves that, say, go in the first quadrant. So that's when we have x's and y's positive, or they might be in another quadrant where x's and y's might be positive or negative. Either way, we have some region that's bounded by some curves. And we then want to rotate that around an axis to work out what is the volume of that solid, okay? So here we're told that we've got a region bounded by these two functions here and the x-axis. Or rather, we're going to rotate this around the x-axis, okay? So let's think about sketching these things, first of all. So what are we going to have here? Let's first of all sketch f of x is equal to 2 minus x. A lot of people have difficulty sketching graphs. Tips to do this, think about when it crosses the axes, so when it crosses the x and the y axes. Think about substituting values in. Okay, so it will cross the y-axis when x is equal to 0. When x is equal to 0, this is equal to 2. So I know that it has to pass through this point here to 0. When is this equal to 0? So when is 0 equal to 2 minus x? In other words, when is y equal to 0? We just arrange that. Again, we're going to have x is equal to 2 here. Sorry, this should have been 0, 2, and this is 2, 0. So I know it has to go through these points. I can also tell that as a gradient of -1. I could substitute other values in here. I could think about what happens when f is 1. I have 2 minus 1 is 1. If this was something that was non-linear, I could think about what happens as x tends towards infinity, or x tends towards minus infinity, or what happens as x tends towards 0. And like I say, you can plug in different values, okay? So this is how we go about sketching curves if you're not sure what they look like. In this case, this is just going to be a straight line that goes through these points here. Oh, didn't want to do that. Okay, so a straight line like this. And our other curve, or our line in this case, is g of x is equal to x. So this is just the line y is equal to x. So that looks like this. So this is my g of x. This is my f of x. Okay, so we're told that we want to create a volume which is bounded by these curves. So the region bounded by these curves here is going to be this region that I've shaded here. So the left-hand side is going to be 0. We don't know what this is here. But at that point, we're going to have f of x is equal to g of x. So we just equate these things. You have 2 minus x is going to equal x. So 2 is going to equal 2x. So x is going to equal 1. Okay, so if you don't know what that point is, you just need to equate them because that's going to be where they intersect. Okay, so what we're doing is we're rotating the shaded area 360 degrees around the x-axis. I'm not going to have a go at attempting to draw that. I'm not very good at drawing things in 3 dimensions. How do we work out the volume of this? Well, the volume of this is going to equal pi as by the integral between our bounds. Our bounds are 0 and 1. They might not always be 0 and 1. Often I'm choosing 0s and 1s just because that makes the math easy. But in general, it's whatever your start and end points are. And then what we're doing is we're thinking about lots of little disks or washers that are created as we move along the x direction. We can think about the area of each of those washers as being pi r squared. Or rather, if we think about the outer one, I'm going to call this RF, corresponding to this F. As we sweep this F around in 360 degrees, that will create a solid on the outside. But then we're also going to want to subtract this highlighted area here, because that isn't part of our solid. So we also want to think about pi times by RG squared. In the notes, I talk about R out and R in. It's the same thing, it's just labels. So thinking about sweeping around what is the total solid created by, that is defined by this outer curve or outer line in this case. And then we're subtracting the whole that we're taking out of it, which is defined by the inner one. Okay. So that means when we calculate our volume, we do pi times by the integral of our outer curve, which is f of x. And we're squaring that because this is giving us our radius, our outer radius. And we're subtracting our inner radius squared, so g of x squared. And this is done with respect to x. Okay, have a go at solving that. Okay, eagle-eyed among you, very good question I had was, why do we not calculate the volume based on this area down here? It's a very good question because the question's actually misworded. When I've written this question here, I should have said that the solid is created by revolving the region bounded by f of x, g of x, and the y-axis. So apologies then if you've tried this before. So basically I've got 2 sides to it and I've not told you what the third side is. So that is a poorly worded question there. I will correct that for next time. But in this case, yeah, you would be given exactly what it is bounded by. Okay, there might be cases as well where it's not bounded by an axis, where it's just bounded by the curves itself, which is typically what I've given you guys, for example, in the IQ. I think here, because I went for linear ones, it wasn't bounded by something. Yeah. Not necessarily, because you could be doing the pink solid, what's created by the pink solid or by the blue solid. The question doesn't state, it says around the x-axis, but it doesn't state where the third side is. So the question should state but you don't know whether you don't know whether you're this one or this pink thing here, right? Because this is also a region that is bounded by the green and the red lines. So it needs a third side. Okay, so you should have got pi times phi, the integral of f of x squared is going to be 2 minus x squared. G of x squared is just going to be x squared. So if you expand that bracket, you'll get 4 minus 4x minus, plus x squared.
Yeah.
And you'll also have a minus x squared from this term here. So these x squareds will cancel. Integrate those, and you'll have 4x minus 2x squared evaluated between 0 and 1. We don't have to worry about the 0 ones here, so those are going to disappear. So we're just going to have pi times pi. 4 minus 2 is 2 pi. And to be fully correct, we should say units cubed, whatever our units happen to be here. There weren't units specified in the question, but it's always good to just put to indicate, because this is a volume, that it'll be units cubed. Okay. Thank you to those who spotted the mistake in the question. Okay. There's only about 9 minutes left, so we're just going to quickly go through this linear systems question after this question here. You wouldn't have to, I'm not going to ask you to integrate anything that doesn't have a power in it.
Okay.
Okay, so I've kept things simple. Okay, linear systems. We've been through a lot of linear systems. We've been through a lot of phase planes. I know that. It is a case of practice, practice, practice. A bit quiet, please, guys. So we went through examples of Romeo and Juliet. This is an example of a linear system, okay? So there's nothing particularly special about these Romeo and Juliet cases. They're just linear systems and a way of illustrating particular dynamics when it comes to something like behavior, okay? Okay, so remember, we were treating these R or J values being greater than 0 as being Romeo and Juliet in love, and negative values as them hating each other. Or disliking. It's not as strong as hate. And here we've got a slightly different setup to what we had before. So Juliet is a cautious lover, but Romeo does not pick up on her signals. Okay, we're told that this is our model here. So we can convert this into a linear system, into a matrix equation, sorry, by setting our vector x to be Rj. As always, it doesn't matter on the order of this as long as we're consistent. We could do JR instead, in which case the rows of our matrices would be changed around in the columns. Here we're going to have -1, 0, 1, -2. So these are just the coefficients in front of my R's and J's. Okay, so here we're asked to classify the equilibrium. There's only one equilibrium at 0, 0. This is a linear system where we're going to have one equilibrium, unlike our nonlinear systems where we can have more than one equilibrium. So how do we do this? Well, we can just look at the trace, which is going to be -1, -2. It's -3, that's negative. And our determinant, which is going to be -1 times by -2 minus 0 times by 1. So it's going to be 2, so that's positive. As you noticed on the formula sheet for the midterm, I give you that diagram with the trace and the determinant telling you what the behavior is. So we've got a negative trace and a positive determinant, which means that we've either got a stable node or a stable spiral. And whether it's a spiral or a node depends on whether we have real or complex eigenvalues. We need to look at what's called our discriminant, the tau squared minus 4 delta. So square our trace and subtract 4 times the determinant. So we're going to have -3 squared minus 4 times by 2, 9 minus 8, which is greater than 0. So our eigenvalues in this case are real. And since tau is less than 0, we have a stable node. So this question here, part B, will Romeo and Juliet eventually find love? Well, this is an interpretation question. I tried to put these towards the end of a question. So you've done some analysis on a model. You've come up with an answer that we have a stable node, but what does that actually mean for an interpretation? Any ideas? So 0, 0 is a stable node. So in the long term, we tend towards 0, 0. So what does that mean for Romeo and Juliet's relationship? Sorry? No? Any other? Someone at the back? Yeah. Okay, so yeah, they don't find love, but neither do they hate each other. So like all good long-term relationships, they tend towards indifference. Hey, I'm British. This is what we do. So it's a very downbeat look at love. They tend towards indifference in the long term. They neither love each other nor they hate each other. How depressing. Okay. I've left space here to do the phase plane. You know that it's a stable node. I'll leave that as a practice for you guys. I will upload the solutions for that because there's not much time left. Again, remember we find just a couple of tips for these. Find your null lines, which you should be familiar with by now. Your direction field. Guys, just 2 minutes, okay? Your direction field, well, if actually, first of all, with your null lines, if I'm say putting J here and R here, I tend to write my null lines as J is equal to something and J is equal to something, okay? You don't have to do that. The reason I do that is because it helps me make sure that the gradients of my lines are clear. This is just like writing Y is equal to some function of X. If you had R is equal to something and J is equal to something, you might get your gradients wrong. You might draw the wrong thing. So that's why I tend to do it like that way. Just 1 second, I will get to you. The other thing I'd say is when you do your direction field, if you're not sure about things, go back and compare it to what you get from your trace and your determinant and potentially your discriminant as well, okay? If you have your arrows pointing away from your origin, but your trace and determinant tell you that it's a stable node, you've made a mistake. So go back and check it. Sorry, that you and then you, okay? If you want to do the eigendirections, then that's fine. We haven't really focused on that, but it's also perfectly legitimate. Yeah, sorry.